Hi everyone. In the previous class, we have derived the current response for series RL circuit. So this is where we have stopped in the previous class. I is equal V by R in minus V by R into e power minus R by L into t. You can rewrite the same equation as I is equal V by R of 1 minus e power minus R by L into t. If you see this equation, it consists of two parts. So this V by R is called steady state part, and V by R into e power minus R by L into t is called transient part, because as time tends to infinity it will reach to the 0. That's why it is called transient part, whereas V by R is independent of the time. That's why it is called steady state part. When the switch S is closed in the circuit diagram, so what is the circuit diagram? DC source, then it is connected with the switch, series RL circuit. When the switch S is closed, the response, that is nothing but current response, reaches to a steady state value after a time interval as shown in the figure. That means after some time it will reach to the steady state, so that waveforms will draw. So based on this equation, the steady state part V by R, right? So transient part is nothing but V by R into e power minus R by L into t, and total current is I. These three waveforms will draw in this graph, in this figure. So V by R is constant, means this dotted line shows the V by R line, and E transient part is nothing but V by R into e power minus R by L into t. By neglecting that sign, if you see at t is equal to 0, in transient part V by R into e power minus R by L into t, if you substitute t is equal to 0, e power 0, which is equal to 1, V by R. At t is equal to 0, it has to start from V by R. Then when t tends to infinity, e power minus infinity. E power minus infinity is nothing but 1 by e power infinity, which is nothing but 1 by infinity. 1 by infinity is nothing but 0. That's why it is going to 0 as time tends to infinity. On y-axis I have considered the current response. On x-axis I have considered the time constant. So how do we get this time constant? That also we'll see further. So as of now, the transient curve I have drawn here, transient part of the curve. And if you see that the steady state is nothing but V by R, that V by R curve also I have drawn, dotted line. And if you see the overall current from V by R curve, we have to subtract this transient curve. V by R is nothing but dotted line, and the transient curve is nothing but this exponentially decaying. If we subtract this exponentially decaying from this dotted line, we'll get the waveform like increasing waveform, which is nothing but V by R into 1 minus e power minus R by L into t. Even in this waveform, if you substitute t is equal to 0, when you substitute t is equal to 0, 1 minus e power 0, e power 0 is equal to 1, 1 minus 1, which is equal to 0. It should start from 0, and when t tends to infinity, e power minus infinity, the second term will become 0. E power minus infinity is nothing but 1 by infinity, 0, and the first term is nothing but V by R into 1. It will reach to the V by R. That's what, from the equation we can get the current, total current as increasing function like this. This is the waveform for total current I and transient current V by R into e power minus R by L into t. So here we'll define this transition period. What is the transition period means? It is defined as the time taken for the current to reach its final value or steady state value from its initial value. What is the current initial value? Initial value is 0. When time t is equal to 0, we can find out the initial value. When time t tends to 0, the second part e power 0, 1 minus 1, it is equal to 0. When time tends to infinity, that is final value, which is equal to 1 by R. So from initial value to final value, how much time it is taking? So that corresponding transition period is nothing but the time taken for the current to reach its final value or steady state value. We'll call that steady state value or final value, which is equal to V by R. So if you see what is the time constant, to define the time constant, I can define the time constant by using this transient equation or overall current equation. So if you see this transient current equation, the time constant of a function v by r into e power minus r by l, or the time constant of a transient function is the time at which the exponent of e is unity. Where is this exponent? Exponent of e should become 1 or unity. When will it become 1? When you write this as, when you substitute t is equal to L by R, it will become unity, right? R by L into L by R. So in that way we can mention the time constant. We'll see further. Where E is the base of the natural logarithm, in this E is the base of the natural logarithm, the term L by R is called the time constant and it is denoted by tau, because by substituting this L by R in this equation, e power minus r by L into t is equal to L by R, if you substitute, then it will become e power minus 1. So where e power becomes unity, the corresponding time is called the, or the corresponding function is, the corresponding value is called the time constant. The corresponding term is nothing but tau is equal to L by R seconds. I can write how many time constant, because here I have mentioned 1, 2, 3, 4 up to 5, 6. Then after 5 it is reaching to the 0. After 5 it is reaching to the v by r, like that I have mentioned, right? Why I have mentioned these numbers means based on this time constants only. Now if you see here, the overall current I is equal v by r into 1 minus e power minus t by tau, because here I have mentioned, I have rewrite that equation, I is equal to v by r of 1 minus e power minus r by L into t. This e power minus r by L into t, I can write it as v by r into 1 minus t by this r, also I will take it to the denominator, so that L by r, L by r. So this L by r is nothing but time constant. That's why I am replacing 1 minus e power minus t by tau. So if you see in this, the corresponding transient term is nothing but the second part, which is having time function. The transient part of the solution is nothing but ITR is equal to minus v by r into e power minus t by tau. Now I will substitute t is equal to 1 tau, t is equal to 2 tau, t is equal to 3 tau. Like that, if I substitute, when that response will reach to the final steady state value, that we'll see. At t is equal to 1 tau time constant, 1 tau is nothing but 1 time constant. If you substitute that value at t is equal to 0, first we'll see, at t is equal to 0, the corresponding transient response is nothing but initial value. By substituting t is equal to 0, minus v by r into e power minus 0 is nothing but e power 0 is equal to 1 minus v by r. Initial value is minus v by r. By neglecting this sign, I'll consider only v by r. For transient, the initial value is v by r, and final value by substituting t is equal to infinity in this transient response, minus v by r into e power minus infinity. E power minus infinity is nothing but 1 by infinity, which is equal to 0. That means for transient response or transient current of initial value, final values are v by r and 0. So you can see in the same graph also, transient current, initial value, final value are v by r and 0. And how can we define the time constant? Means at t is equal to 1 tau, at t is equal to 1 tau, the transient term reaches to the 36.8% of its final value. How it will reach to the 36.8% of its final value? Means by substituting v by r into e power minus tau by tau, which is equal to v by r into e power minus 1. This e power minus 1 value is nothing but 36.8% of its initial value. Initial value is nothing but v by r, right? What is the initial value here? V by r. So if we substitute 1 tau time constant, the response will reach to the 36.8% of its initial value. In a similar way, if we substitute 2 tau in the same response, it is 13.5 percentage of V by R, 3 tau e minus V by R into e power minus 3 tau by tau, which is equal to e power minus 3, 4.98 percentage of VR. If you substitute 5 tau, e power minus 5, which will give 0.6 percentage of VR. That means it is almost reached to the steady state. That's why after 5 tau time constant, the transient part will reach us to the more than 99% of its final value. What is the final value? Final value is nothing but 0. It will almost reach to the 0. That's what after 5 tau time constant. That's why we'll draw the waveform from 1 tau time constant to 5 tau time constant, then later it will reach to the either 0 steady state or final value of that corresponding responses. For current, final value is nothing but V by R. For transient current, final value is nothing but 0. After 5 tau time constant, it is reaching to the 0. After 5 tau time constant, current is reaching to the V by R. It will reach to the corresponding final values. Even the same analysis you can do it with for the overall current also. In overall current also, I of tau you can substitute, which is equal to V by R into 1 minus e power minus t by tau. T is equal to tau. So which is equal to V by R into 1 minus e power minus 1. So e power minus 1 is equal to 0.368. That you can substitute here, V by R into 1 minus 0.368 like that. So you'll get 0.632 of VR. That is 63.2 percentage of final value. So if you take the overall current by substituting one tau time constant, it will take 63.2 percentage of final value, because for overall current the final value is nothing but, if you see the waveform, for overall current the initial value is 0, final value is V by R. So it will take 63.2 percentage of its final value of V by R. Like that, in a similar way you can substitute 2 tau, 3 tau, 4 tau, 5 tau. After 5 tau it will almost reach to the 99.9% of its final value. That is nothing but it is close to the final value. So next, after we get that current response, now we'll find out the voltage across resistance. What is the voltage across resistance? VR is equal to R into I. R into I current is nothing but V by R into 1 minus e power minus R by L into T. R will get cancelled. VR is equal to V into 1 minus e power minus R by L into T. In a similar way, we can find out the voltage across inductor. VL is equal to L into di by dt, L into d by dt of I. I current is nothing but again V by R into 1 minus e power minus R by L into T. By doing this, V by R is constant that I am taking out of this differentiation. By doing the differentiation of 1, 0, differentiation of e power minus R by L into T is nothing but e power minus R by L into T by minus R by L. That coefficient will come in the denominator, minus will get cancelled. R, L and L will get cancelled, R by L, so will get cancelled. So finally the remaining terms are VL is equal to V into e power minus R by L into T. I can draw the waveform for VR and V also. VR is nothing but V into 1 minus e power minus R by L into T. It is similar to the current waveform, right? We are multiplying the current waveform, current with the resistance, just magnitude will increase. That means it will follow similar to the current waveform. By substituting T is equal to 0, you will get the 0 volts. By substituting T is equal to infinity, you will get the V volts. So actually it is not V by R, it is V volts. That V curve is nothing but the constant line. It will reach to the V when time tends to infinity, because when time tends to infinity, the second term will be 0, only remaining term is V. So this is what VR. And VL curve, if you see, when time tends to 0, e power 0, which is equal to 1, it will start from V. When time tends to infinity, e power minus infinity, which is equal to 0. That means it will reach to the 0. VL curve is exponentially decaying, VR curve is increasing. And if you know the voltage and current equations, you can derive the power equation. the power in resistor PR is equal to voltage across resistance into current. Voltage across resistance already we have derived, which is equal to V into 1 minus e power minus R by L into T. V into 1 minus e power minus R by L into T into current waveform. Current is nothing but V by R into 1 minus e power minus R by L into T. By multiplying these two, we'll get V square by R into 1 minus these two terms, that is nothing but minus 2 into e power minus R by L into T, minus into minus, it will become plus, and both bases are same, powers will be added, e power minus 2R by L into T. In a similar way, power in inductor is nothing but voltage across inductor into current. Voltage across inductor is nothing but V into e power minus R by L into T into current is V by R into 1 minus e power minus R by L into T. By multiplying these two, V square by R into E into this one, E into minus R by L into T, bases are same, e power, powers will be added, minus 2R by L into T. So we can draw these power waveforms also. Power in resistor is nothing but we are multiplying the voltage waveform and current waveform. Both voltage in resistor and current waveform are in a similar line, the same waveform, right? In a similar way, the current waveform with lesser magnitude it will be there, right? So when both are getting multiplied, then the power line also in a similar way, it will be with little higher magnitude. So what is the constant term here? V square by R, because when time tends to 0 means t is equal to 0, t is equal to 0. So I will get it as V by R is the initial value, only V by R is the independent of the time. So that's why power curve, it will follow similar to the voltage and current curve. And if you see the power in inductor, V square by R into e power minus R by L into T, e power minus 2R by L into T. So voltage across inductance, if you see, voltage across inductance is decaying function and current is increasing function. We have seen the current function also, right? Current waveform also. That current waveform is increasing function. This current waveform is increasing function and voltage across inductance is decaying function. So that initially the current is 0, voltage across inductance is maximum. That means your power in inductor will be equal to 0 into maximum, that will become 0 again. And if you see the current is reaching to the V by R, whereas voltage across inductance is reaching to the 0. 0 into V by R, again 0. That means both starting point, ending point of the power in inductor, if you see, 0 and 0. In between, both current and voltage across inductance will reach to some value. When you multiply, it will reach to the maximum. That's why power will go to the maximum, then it will reach to the 0. This is all about the DC response of series RL circuit, and where we have seen the complete analysis of current response, voltage across resistance, voltage across inductance, power in resistance and power in inductor. So based on that derivation, we'll see one problem also. If you see the problem, the statement is a series RL circuit with R is equal 30 ohms and L is equal 15 Henry has a constant voltage V is equal 60 volts applied at T is equal 0 as shown in figure. This is the figure. Determine the current I, the voltage across resistor and the voltage across inductor. 60 volts is connected to the series resistance and inductor through the switch. The response is current response. What is the first step when you get this type of problems? The first step is apply KVL and find out the differential equation. By applying KVL, 60 is equal to 30 into I plus 15 into di by dt, L into di by dt. You have seen with the derivation also, right? I can rewrite this equation like di by dt plus, I am dividing on both sides with 15. 30 by 15 into I, 60 by 15, which will get it as di by dt plus 2i is equal to 4. This is the first step. First I found the differential equation that I have marked it as first equation. And second step, you can compare the same thing with the known differential equation. The known differential equation in mathematics is dx by dt plus pi is equal to k. That I am marking it as second equation. By comparing these two, your x is equal to I, p is equal to k is equal to 4. X is equal to I, p is equal to k is equal to 4. For the known differential equation, the solution is nothing but x of t is equal to e power minus pt integral k into e power plus pt into dt plus c into e power minus pt. If you compare these two equations, we got these terms. You can keep the same substitute in this solution so that you will get the solution for the first equation also. I of t is equal for this first equation, the solution based on this equation, based on the solution, I of t is equal to e power minus 2t, p is equal to 2, e power minus 2t integral 4 into e power 2t into dt plus c into e power minus 2t. So by integrating this one, the 4 is out of this integration as it is constant, e power 2t by 2 after doing the integration plus c into e power minus 2t as it is. So e power minus 2t into e power 2t, base is same, powers will be added so that you will get the e power 0 which is equal to 1, and 4 by 2 is equal to 2. 2 plus c into e power minus 2t is the third equation. This is the third step. From the third step, we need to get this current equation. From the first step, first differential equation, second step, known differential equation for the comparison, third step, find out the current equation from that solution. And in this current equation, if you see one arbitrary constant c is there, that you have to find out. If you find out, that is the fourth step. To find out that c value, use the initial conditions. What are the initial conditions? At t is equal to 0 minus. Earlier or in the past, the switch is open in this circuit. When switch is open, the current flowing through this inductor or loop current is equal to 0. That's what I have mentioned. I of 0 minus is equal to 0 ampere. When switch is closed at 0 seconds, the switch remains closed at 0 plus also. Because of the inductor property, inductor do not allow the sudden, even though switch is closed, the inductor do not allow the sudden change in current. That's why the current remains same with 0 ampere and 0 ampere at 0 and 0 plus also. However, the switch is closed, but the current will carry, the same current will carry through the inductor. That is equal to the loop current. By using these initial conditions, I will substitute this initial condition I of 0 plus in this third equation. I of 0 plus is equal to 2 plus c into e power minus 2 into t at t. I will substitute 0 plus. 0 plus is nothing but 0. 2 into 0 is equal to 0. E power 0 is nothing but 1. That is equal to c. 0 is equal to 2 plus c, because 0 is nothing but I of 0 plus is equal to 0. That's why I am substituting on left side also 0. From this I will get c is equal to minus 2. I will substitute this c is equal to minus 2 in the third equation to know the complete solution. I of t is equal to 2 minus, in place of c I will substitute minus 2 into e power minus 2t, which is equal to I of t is equal to 2 into 1 minus e power minus 2t amperes. Further, we have to find out the voltage across resistance. Voltage across resistance is nothing but R into I, where R is equal to 30 and I equation already we got it as 2 into 1 minus e power minus 2t. So 30 into 2 into 1 minus e power minus 2t, which is equal to 60 into 1 minus e power minus 2t volts. Now we need to find out the voltage across inductance. VL is equal to L into di by dt. L is equal to, from the figure, 15 Henry. 15 into d by dt of I equation is nothing but 2 into 1 minus e power minus 2t. 2 into 1 minus e power minus 2t. 2 is constant, that I will take it out of this differentiation. 15 into 2 is nothing but 30. Differentiation of 1 is 0. Differentiation of e power minus 2t is nothing but minus 2 into e power minus 2t. Minus into minus will become plus. 2 into 30 is 60 into e power minus 2t volts. Voltage across inductance is nothing but 60 into e power minus 2t volts. So by following the derivation, we can do it in a similar way. This type of problems also. The derivation, the similar kind of problems we have solved in this class. Thank you all.